I'm going to talk, I'm Technical Director of Alpha Data. I guess my talk is going to be focused on, I guess, the HBM parts that you've heard about an awful lot in the last talk. I'm also going to touch on OpenPOWER. I'm going to talk about some of the hardware we've been working on, primarily for the OpenPOWER side of things, but also based on these HBM chips. I'm going to talk initially about some applications that have used these parts, and then I'll go on show some sort of architecture, some shell structures that you can put in the FPGAs to work with these, and then I'll go on and present some of information about some of the hardware we've brought to the market based on HBM products. So, quick overview. First section, I'll just briefly recap on the HBM architecture. Previous talk probably told you far more detail than I've got time to go into, so I'll just briefly touch on that, and again I'll also briefly touch on some of the reasons why FPGA acceleration gives you performance increases over other architectures, despite the fact that possibly other architectures might have hardened arithmetic or operational units that are potentially higher performance than FPGA implementations. I'll then go and talk about 4 or 5 different applications that we've looked at, certainly at a simulation level and a implementing of a Vivado level on targeting the HBM architecture. I'll then look at some sort of in-chip architectures, some shell designs that might fit these different architectures, and then I'll talk about some of the boards that we've brought to market, specifically ones in the data center and OpenPOWER area. So I guess the only thing I really want to say about the HBM architecture that hasn't already been covered, or has been covered probably quite well so far, the key point really is the fact that you've got this massively wide bandwidth interface, but you have to access it as 32 independent ports, and these are fortunately quite well spread across one of the HBM dies, so you've got less routing congestion issues in using these, and each of these ports does allow, through the switching IP, allow you to access all 8 gigabytes of the on-chip memory, and that allows you great potential in parallelizing your architectures. I guess quickly run through why FPGAs give you improvements in performance per watt and performance per gate. A lot of the improvements improve just efficiency of your implementation. These can be data flow pipeline processing. You're feeding data directly between your operational units, your arithmetic units. You're not storing them in any intermediate caching. You don't need to implement an instruction set, so you can save all the extra power cost and memory access cost of running an instruction unit. You can reduce your arithmetic complexity down to a level that's actually needed for your algorithm, and you can actually have very detailed control over your application-specific memory management. You can schedule your memory reads and writes to actually match what your application needs, and also access the hardware in the most efficient manner. With all these implementation efficiency improvements, that allows you to parallelize massively across your chip, and that gives you your performance increase overall. However, all this acceleration within the chip, you're still going to hit an I/O bandwidth boundary because your external chip has not increased in bandwidth for a number of years. However, HBM is one area where you're going to get an order of magnitude improvement in this area, so this is one thing we're looking forward to. So I'll move now on to some of the machine main applications that people are targeting FPGAs with. Probably in 2018, you probably couldn't have a FPGA talk without mentioning machine learning, artificial intelligence. These can be most energy efficient if you can keep your neural network weights within the chip in your on-chip cache or your on-chip ultra RAM or block RAM. As soon as you move these data around, that's obviously, some of these can be very large, and that can be a quite high energy cost. But unfortunately, some of the networks that people are coming up with are too big to fit on any chip. I think probably the best example, I think VGG network is the largest one. So your options are to go to multi-chip, which might be an option if you're Amazon or you're Microsoft, but it can be a very expensive option, or you can use external DRAM. The memory bandwidth for getting your weights on and off the chip is pretty high, but you can make this efficient by using batch process, and reduce, the number of and process a large number of images or elements or input data sets as a batch, splitting up the network processing. However, this type of solution, which is quite good if you've got a single FPGA and external DRAM, is going to be memory bound unless you can use large batch sizes, and you might not want to use large batch sizes because the larger the batch size, the worse your latency. So again, HBM should give you your order of magnitude performance boost over your standard DRAM-based accelerator. Some other applications we've been looking at, we've been looking at search. That's a fairly trivially parallelizable and memory-bound type of applications. FPGAs give you great potential to scan the same data set multiple times for lots of different search queries, just streaming the data in and out as fast as possible. That's obviously memory-bound and obviously going to benefit from HBM. We've looked into sort, and you can implement in FPGAs a order-in parallel merge sort. You can basically just stream the data straight through different sorting FIFOs in an almost FFT-like comparison, split and merge type algorithm. This will hit your memory limit of about 60 megabytes using ultra RAM and block RAM, but if you've got all these multiple HBM ports, you can then actually set up higher order merges going to and from HBM in a streamed sequential manner that will efficiently access the HBM. Another thing we've looked at in terms of big data type data analytics is k-means clustering. Again, this works well with fixed point implementation because your data sets have to be normalized to more or less the same scale and don't benefit from any unequal numerical distributions. And again, this is easily parallelizable. Most people want to run this multiple times with different starting values. And although not necessarily memory bound, this will become memory bound if you want to run lots in parallel or you have very large data sizes. We have looked at a couple of other applications. I didn't set up Alan with the question earlier, but we have looked at 3D FFTs, and see, look at these big FPGAs. Ultra RAM's going to be good for corner turning memory, probably up to 128 cubes of double precision, or I suppose bigger with smaller. HBM can be used for corner turning, although not directly. I think you need to use ultra RAM as an in-between cache. You would parallelize your reads across multiple channels. But this would give you a corner turning memory up to 8K FFTs cubed. Should just, I think, occupies about 4 gigs each, so you've just about got enough memory to swap it. Again, we've looked at matrix multiply, although not specifically memory bound. You pretty much, when you do a memory multiply operation, you usually follow up with some sort of memory bound operation like an add if you are sort of dealing with a larger size of memory matrix and trying to combine them, or I guess a lot of other high performance computing applications tend to perform multiplications and then scalar multiplies or square roots or other memory bound linear operations. So there's a potential to use HBM, the multiple port options of HBM to manipulate this data in a higher bandwidth way in parallel or as part of the same algorithm and same library as the matrix multiply. So on to the sort of the HBM accelerator type shells. This first example is probably very similar to what was presented in the last talk. Is kind of the standard OpenCL type shell where you shift data from the host memory into the the working memory on your accelerator card and then process it from there. This is going to be quite effective for if you're working data sets between 50 megs and 8 gigs. If it's 50 megabytes, you might as well put it in your ultra RAM. You probably don't want to move it into even HBM. You can use a faster memory. If it's greater than 8 gigabytes, you are going to hit the PCIe is going to be your bottleneck. So this solution will work for quite a lot of use cases, but there are ways we can go. Obviously, I've mentioned PCIe bottlenecks, and I suppose Myron spoke earlier about how people are working around the PCIe bottleneck, and OpenCAPI is certainly a solution that allows you to jump beyond this, not only giving you a big jump in bandwidth, but also lowering the latency and giving you all the advantages of cache coherence. So this type of solution would allow you to extend your working memory from just your 8 gigabytes HBM to also use with a slightly lower performance your host memory as part of your accelerator action memory. And this would, the differences between standard DDR4 on the board and the coherent most memory over using OpenCAPI, they're still within the same order of magnitude. So possibly in this case, you might not want to use onboard RAM when you might have 128 or 512 gig of host memory, which can also be shared coherently with the CPUs. And when we're looking at HPC type applications, multi-node systems, what we're thinking is what you want is high level of connectivity from your HBM to other equivalent accelerator nodes, and sharing the data directly between these nodes. And so, the high performance GTs that we have in Xilinx type FPGAs allow you to share this, and you could have many links between nodes, extending your working set sort of horizontally across the different FPGAs rather than just extending it through host memory. And you can actually come up with a very similar architecture for networking, which I guess is maybe possibly related to Enric's question as well. And here you could have your 100 gigabit Ethernet all feeding into an HBM working memory, and this being matched by an OpenCAPI transfer to the host memory. And while this data is sitting in your HBM working memory, you could have a lot of intelligent type network analytics applications performing threat detection and other types of networking algorithms accessing that memory and deciding to throw away packets or discard them. So finally onto the sales type plug. Alpha Data have been working with the VU37P to bring our own board to market, and we've looked at these different areas and identified what we should have. We've targeted the sort of the full height, 3/4 length, double width PCIe form factor that GPUs typically have, and people asked about power just earlier, and we've spec'd this up to be able to take and cool 225 watts. Possibly most users will never drive the chip up to that level. Again, the key I/O features of this is we have 4 QSFP28 100 gigabit Ethernet capable interfaces at the front. We have PCIe Gen 3 or Gen 4 by 16 on the edge. The Gen 4 would be bifurcated as 2 Gen 4 by 8s. We have 2 OpenCAPI capable connectors to the rear of the board, and we also have 8 onboard 28 gigabit per second capable Firefly connectors. And these Firefly connectors are quite interesting because they give you a number of expansion options. You could connect them between 2 cards equally if you were wanting to transfer data between HBM chips. You could also connect direct to, say, in-chassis storage, such as you could run NVMe PCIe over the Firefly. And the example shown in this slide is our expansion card that we've come up with, which is a single slot PCIe card, which allows you to connect an additional 4 QSFP connectors out using per extra PCIe slot. We do have a number of other boards which are not HBM enabled. The one illustrated here is the VU3P, which has been imported in the OpenCAPI bring up. This card is effectively an OpenCAPI FPGA NIC card with the VU3P Vertex UltraScale device on it, and it's capable of OpenCAPI and CAPI 2.0 operation. It has two QSFP 28 front connections, which are each capable of 100 gigabit Ethernet, and this board has a onboard DDR4 and has the OpenCAPI interface at the back. And we think there's quite a good match between the 2 by 100 gig Ethernet at the front and the 25 gigabit per second capability of OpenCAPI. Also like to mention a couple of our older boards which are Power 8 and CAPI Window O capable. The KU3 and the 8K5 boards, these are based on Xilinx UltraScale KU16, KU115, and these are both CAPI Snap enabled, and you'll hear more about CAPI Snap later. So these are capable of networking as well, and there'll be a talk tomorrow on CAPI Snap networking, and these cards are capable of 10G or 40G, so they're not quite into the 100G element, but they're possibly a good entry-level solution to get into CAPI development. And then just early announcement of a board we're bringing out fairly soon at Supercomputing, the AIDA PCI 9H3. This is a low-profile version of the HBM card. It has the VU33P device, and it has an OpenCAPI connection at the rear. So this could well be a deployable OpenCAPI NIC card. Has the QSFP DD connection, allowing you 200 gigabit Ethernet connections out the front. And really just to summarize, I think I've seen from the previous talk and everything else that HBM is offering a magnitude improvement in memory bandwidth for FPGA applications that hit that issue, and you can see that there's a potentially good fit between HBM and OpenCAPI, and we have boards available for both of these technologies. So I'll just get into, if there's time for questions, it's great. If not, we're at the booth.